Welcome back. In this last section, we're going to be doing a little bit more examples of graphing with transformations, and then we're also going to talk a little bit about symmetry for graphs. So here I've got an example where instead of having the function given to me, I tell you what the basic shape is and then what we're doing to it. So I'm starting with my graph of x squared. I shift it to the right. I stretch it vertically by a factor of 2, and I also reflect it in the x-axis, and then I shift it upwards by 2 units. So if I'm looking at this, I can see that actually what I'm doing is all of my transformations to my basic shape in the order that I'm supposed to do them. I'm shifting first horizontally, then doing my vertical stretch and flip, then doing a vertical shift afterwards. So for this, it's not too terribly difficult for me to write out what my equation of g of x should be. I have my shape x squared, and we're shifting it to the right by 3 units. So instead of x squared, it should be x minus 3 squared. That would be shifted to the right. If we're stretching it vertically by a factor of 2, there needs to be a 2 in front. And if it's also a reflection, then really it needs to be a negative 2. And then finally, shifting it upwards by 2 units means that there needs to be a little plus 2 at the end. So now that I've got all that equation figured out, I can do my graphing without too much difficulty. Start with my basic shape, y equals x squared. Then next, I'm going to be shifting it to the right by 3. So I'm going to be adding 3 to all of my x values. So instead of 1, 1, I'll have 4, 1. Instead of 0, 0, I'll have 3, 0. And instead of negative 1, 1, I'll have 2, 1. Of course, we need to label that. So that is x minus 3 squared. So we've done part of our work. We've done the first transformation, the shifting to the right by 3. The next transformation, the stretch and flip, I'll do both of those at the same time. I'll multiply all of my y values by negative 2. So taking my last graph that I have and going and multiplying all the y values by negative 2, instead of 4, 1, I'd have 4, negative 2. 3, 0 will stay where it is because when I multiply the y value by anything, it stays as a 0. And 2, 1, I multiply the y value by negative 2 to get 2, negative 2. So we've now taken our function and we've stretched it and flipped it. So this is now negative 2 x minus 3 whole thing squared. And then the last transformation that we had was a shift upwards by 2 units. So I'm going to take those 3 points that I have and I'm going to add 2 to all of my y values. So instead of 4, negative 2, I'll have 4, 0. Instead of 3, 0, I'll have 3, 2. And instead of 2, negative 2, I'll have 2, 0. And then I just need to label my equation. And I could label this as y equals or g of x equals, depending on how I feel, because of course, as we know, g of x is the y value, so it would be fair to also label this as y equals, rather than g of x equals. All right, so this one's a little bit different because for this one, instead of having a function that's a basic shape that we're then transforming, this is a function that has a basic shape already transformed, and then we're doing some more transformations on top of it. So this is a parabola that's been shifted to the right by 1. It's been stretched vertically by a factor of 3. We've already shifted it up by 2, and now we're doing all this other stuff to it. So for this, I think the easiest way for us to think about it is to start to think symbolically. If you remember at the very beginning of things where I said something like f of x plus k meant a shift upwards by k units, or when I said f of x minus h meant a shift to the right by h units, I'm going to do the same sort of writing here of what my function g of x should be. G of x is the function that we're going to get when we take our function f of x and shift it 2 to the right. So shifting 2 to the right would be f of x minus 2. Shifting it downwards by 1 means I would have a minus 1 at the very end of it all. So in terms of symbols, f of x minus 2 minus 1 means take f and shift it 2 to the right. That's what f of x minus 2 means. And a little minus 1 at the end means shift downwards by 1. So how do I find my function? Well, now I just need to do like we did at the very beginning of chapter 3 and evaluate, find out what is f of x minus 2. And I know how to do that. I'll take my function for f of x and I'll replace the x that I have in it with x minus 2. And then at the very end of it all, I should have a little minus 1. So everything that I've got here in that little under bracket, that is f of x minus 2. So I've taken my original function and I've replaced the input with x minus 2. And then I have a little minus 1 tacked on at the end to deal with the vertical shift downwards. And then the last thing that I need to do here is just to simplify. There's not much really extra to do other than to say that inside the bracket, x minus 2 minus 1 is x minus 3. And plus 2 and negative 1 gives us plus 1. So same sort of thing here. We have another function h of x. And for h of x, this is going to be the function that we get when we take f of x. And it says we're going to stretch it vertically by a factor of 2. So in other words, we're taking f of x and multiplying the whole thing by 2. So all I need to do then is, exactly like it suggests, take 2 times my original function. So I need to remind myself, my original function f of x was 3x minus 1 squared plus 2. And so I'm now going to multiply all of that by 2. The 3 times the 2 as well as the 2 times the 2, giving me 6 times x minus 1 squared plus 4. The last topic for us to discuss in this section is symmetry of functions. There are two kinds of symmetry. There's symmetry around the y-axis, which happens when we've got what's called an even function. Something that's got that kind of symmetry around the y-axis, is something like y equals x squared. If you're an even function, then you will satisfy this property, that f of negative x is the same thing as f of x. Or in other words, if we change our x value's sign, the y value stays the same. And we see that in our friend the parabola by the points 1, 1 and negative 1, 1. We change our x value's sign, but the y values remain the same. This is how we'll test to see if a function is even. We'll look at f of negative x, and if we have our original function given back to us, then our function is even, and it should be symmetric around the y-axis. The other kind of symmetry is symmetry about the origin, which is something that you'll see in a function like y equals x cubed. Symmetry about the origin, you can kind of imagine it as two reflections. So if I were to think about taking what I've got here in quadrant 1 and reflecting it in the y-axis, then reflecting it again in the x-axis, I'd get what I've got down here in quadrant 3. In other words, I'm sort of reflecting diagonally across the origin, that whatever's in quadrant 1 reflects into quadrant 3, or if I'd had things in quadrant 2, they would have reflected across into quadrant 4. For an odd function, those have the property that f of negative x equals negative f of x. In other words, if we change the sign of the x value, we will change the sign of the y value as well. And we see that with our x cubed graph with the points 1, 1 and negative 1, negative 1. If we change the sign of our x value, we also change the sign of our y value. And just like for even functions, we'll use that to detect if a function is odd. We'll look at f of negative x, and if it turns out to be negative 1 times our original function, then the function is odd and it's symmetric about the origin. You might be looking at these and wondering, what about symmetry around the x-axis? So we have symmetry around the y-axis, we have symmetry around the origin. We don't have symmetry around the x-axis because if you thought about something that was symmetric around the x-axis, like for example this parabola on its side, that would be symmetric around the x-axis, but it wouldn't be a function because it would fail the vertical line test. A vertical line would cross through that graph in more than one place, and that would happen with anything that's symmetric around the x-axis, with the exception of our horizontal line, y equals 0. So that means for functions, there's really only the two kinds of symmetry: symmetry around the origin and symmetry around the y-axis. Before we do some examples for detecting kinds of symmetry, the first thing I want to mention is, even though we're using the words even and odd, and you're usually thinking about things either have to be even or they have to be odd, that's true for whole numbers, but that's not true for functions. For functions, there are three options. A function could be even, a function could be odd, or a function could be none of the above. It could be not even and also not odd. So for example, if I just draw a little zigzaggy kind of a graph like that, this is certainly not symmetric around the y-axis, so it is not an even function. It's also not symmetric about the origin, so it's also not an odd function. This is a graph that has neither kind of symmetry, and that's the typical one that we'll be seeing for most functions. They won't have either kind of symmetry. The last thing for us to note is, for both kinds of symmetry, detecting them involves looking at f of negative x and asking ourselves, do we get our original function back, in which case the function is even? Do we get negative 1 times our original function, in which case the function is odd? And if we get anything else, then the function is neither. It has neither kind of symmetry. Okay, so with this, I know what the original function looks like. If I were interested in negative 1 times the original function, I would have negative x to the 7 plus 3x cubed and minus 1 over x. So when I detect whether this function is even or odd or neither, now I need to ask myself, what is f of negative x? And is it equal to my original function? Is it equal to negative 1 times f of x? Or is it equal to something unrelated? So let's find out. F of negative x means we're taking our original function and replacing all of the x's with negative x's. So instead of x to the 7, it's negative x to the 7. Instead of 3 times x cubed, it's 3 times negative x that's getting cubed. And instead of 1 over x, it's 1 over negative x. If I simplify this, I know that x was going to be, negative x rather to the power of 7 is going to be negative of x to the 7. Any negative to an odd power stays negative, so this would be negative of x to the 7. This would be negative x cubed times the negative 3 gives me positive 3x cubed. And 1 over negative x is the same thing as minus 1 over x. And if I'm looking at this, this is not the same as my original function, so we are not even, but this is the same as negative 1 times f of x, so that means f is odd. So whatever the graph of f of x looks like, we know it should be symmetric about the origin. Okay, so let's do the same thing for g of x and tell whether it's even or odd. I'm going to start same way that I did before by first figuring out what is negative 1 times my function. This is a place where people will make a mistake, and a fairly common one for people to make is when they look at -1 times the function, they will multiply the top by -1 and also multiply the bottom by -1. But remember, -1 is the same thing as -1 over 1. So when I'm multiplying this fraction by -1, really, I'm only multiplying the numerator by -1, not the denominator. So negative g of x is really negative 3x over x cubed plus 1. Okay, so now let's look at what we really want to investigate. What is g of negative x? Is that the same as my original function? Is that the same as -1 times g of x, or is it something else? So g of negative x, same as before, taking my original function and replacing the x's with negative x's. And then simplifying just a little bit. That gets me minus 3x on the top, negative x cubed plus 1 on the bottom. So if I'm looking at this, this is clearly not the same thing as my original function. So number one, g of negative x is not equal to g of x, which means we are not we are not even, rather. Also, this is not the same thing as -1 times g of x. So in other words, it's also not odd. So this function has neither kind of symmetry. It's not even and it's also not odd, which, like I said, that's typical for most functions. They won't have either kind of symmetry. Okay, one last example. So here I've got k of x, and I'm going to do the same thing that I did before. So -1 times k of x, multiplying this function by -1, which is the same thing as -1 over 1, or in other words, it'll change the signs of every one on the top, but the bottom will stay as it is. Okay, so now let's look at k of negative x and see what we get. Replacing all the x's in my original function with negative x's, I'll have 1 minus 3 to the negative x to the 6, all over negative x squared. And for this, since it's a negative number being raised to an even power, I know it's going to come out to be positive. So negative x to the 6 is positive x to the 6. So I'd have 1 minus 3 times x to the 6. And negative x, when I square it, gives me positive x squared. And I can see that I've got my original function back. I can see that k of negative x is the same thing as my original function k of x, which means that k is even. So whatever the graph of this function, whatever it looks like, I know that it's going to be symmetric around the y-axis.